Share screen. So, okay, we're going to continue with the second class of OWL today. So the last time we spoke about logic, or the last two classes, we've spoken about ways of making these logical definitions about the data. We spoke about the RDFS standard, and we spoke about the OWL standard, and we saw some ways in the lab of how to define axioms to allow for inference over the data. So we're going to talk a bit more today about OWL, more conceptual topic in terms of how it's defined. So we saw some examples in the previous class relating to family relations as an introduction to the ontology language, but we just mainly focused on examples. So what we'd like to do today is to explain in a bit more detail how we can define ontologies, right? More rigorously, not just show some examples and say, in this case, that happens, but really define ontologies. And this is important because, of course, we don't want to have any ambiguity about the conclusions of an ontology. So we want to be crystal clear. We want to be very clear about what follows from which ontologies. Of course, this is very important in the case of, for example, medical ontologies, where we don't want to have these any doubts about what the definitions mean, nor about what conclusions can be held from that in various applications, such as mentioning medical ontologies as an example. So we have some definitions here, and we can see that these definitions imply some other data. For example, has child is the inverse of has parent. We have that here. So if we have Carmela has child Michael, then we have Michael has parent Carmela. But where do these inferences come from? So the goal of today is to capture somehow the main ideas of OWL, not to give all of the formal definitions. The standard is quite complex. So, but I would like to get across some of the concepts used in order to define ontologies. In general, that's not to say that somehow this is a rough sketch. Essentially, there's some details that I will gloss over, but I really want to get across the main idea, which I think we can do. So in general, this class and the next class, they're more conceptual, they're more technical. They are essentially just to give you some, they touch upon topics of logic, of philosophy, knowledge, representation, and so forth. Given that it's research, it's a postgrad course on a research topic. I think it's important to talk about some of these more conceptual issues, right? So hopefully these are issues that will make you, maybe make you think in a different way about ontologies and so forth. The labs in general are sort of aside, so most of the labs will be based on the last class, and these two classes are going into more conceptual topics. So defining OWL, how do we do this? So if we look at an example, just to see the problem of why we need to define OWL. So the last time we had a similar example to this using the one-off feature, which allows us to define a class, this class here, which is exactly composed of, which contains precisely these elements here. So Godfather is equivalent to the class containing Vito, Michael, and Vincent. So how can we formally define what this means? So why do we need to do this? So the first reason is because we want to be able to define what follows from such a definition, what we can conclude based on such a definition. We could try with rules like, for example, if C is equivalent to this class here, and this class is composed of all these elements here, then all of these elements here are of type this class. So essentially we would conclude based on this rule that Vito is type Godfather, Michael is of type Godfather, Vincent is of type Godfather, right? But there are other things that this definition means. So we could infer this, right? But if we have, in this other direction, we have someone, we know that someone is of type Godfather, and we know that they're different from Michael and Vincent, then we could actually conclude something here, which is that Vito Young is of type this class, this class is equivalent to the class of these three things here. So essentially the conclusion is that Vito Young must be the same as Vito, right? So there's no other option. We know that this entity is somehow in this class here. And we know it's not Michael, we know it's not Vincent, so it must be Vito. Right? So essentially the point is that we can try to think about defining a rule in such cases, but it becomes very complex because we need to start defining rules that consider all the different definitions of, or all the different semantics of all the different axioms. For example, in this case, we get the conclusion based on a combination of the one of definition and the different from. Right? So it will become, hopefully just to give an idea that it would become very difficult to define all the rules we would need. Well, for example, here in this case, we're assuming that that it's the first element, right? Because we're going to conclude that it's the same as the first element here. So what if it's not the first element? Have we considered all possible cases, all possible combinations of features? Have we, when would we know that our rule set is complete? So the problem we have is that a finite set of rules may not be able to define everything we need in OWL. So essentially, if we tried to write down rules, we could continue arbitrarily writing down more rules and more rules and more rules, and we would never finish. So how can we begin to formally define what classes mean? This is the first conceptual question that we have to tackle. And the main idea, any doubts or questions up to this point? No? Okay, so how can we begin to formally define what classes mean? So there is a bit of a hint on the slide. So if you look at this notation here, you might recognize it as set notation. So how can we begin to formally define what classes mean? We can use set theory. We have set theory from mathematics. It's formed part of mathematics for a long time. There's different set theories, but we can use essentially the notion of set theory. So there is a set of individuals like Vito. Okay, so we're talking about the person in this case, the thing that the name Vito refers to. There's a set of classes. Okay, there is a set of there's a mapping from classes to sets of individuals. Like we can map from Godfather to the elements, the entities in that set, and we can map names to individuals. So we can map from Vito and say that Vito is a reference to this element here is an individual, and this element is in the class of the Godfather. Okay, so when I use the images here, what I wish to refer to is that the data here, these terms, they're assumed to refer to something, right? So essentially, I will use the images to refer to the thing, right? So for example, here, right, we have two different names referring to the same person. Actually, maybe I could use the same image here twice. But when I use the images, I'm referring to the actual thing that the name refers to. Okay. So essentially, what's the idea? We define the class as a set, right? So if we say that A is of type B, then we say A, the individual A is an element of the class of the set that is referenced by that class B. Okay, so we have some names that map to individuals, and we have other names that map to classes. Like Godfather refers to a class. So we can name both the classes and the individuals. Okay, so in this case, we have a symmetric property, a sibling, which means that if we have Connie's sibling Fredo, then Fredo will be the sibling of Connie. Right? So how can we begin to formally define what properties mean? So if we consider classes to be sets, what would we consider properties to be? Well, intuitively, a property would be something like a set of pairs, right? So we already have that there's a set of individuals and classes map to sets of individuals. We're going to extend it and say that there's a set of properties, like this thing here, this icon refers to this property in the real world, this conceptual relation. And what we say is that properties map to sets of pairs of individuals. So this property here maps to all the pairs of individuals that are siblings, effectively, right? So for a class, we have a set. For a property, we interpret it as a set of pairs. Okay. So now we can map names to one of three things: to individuals, to classes, and or properties. Right. So we can name classes, we can name individuals, we can name properties. Okay. So we have an individual, which is just an element of a set. We have classes, which are sets of elements, and we have properties that are sets of pairs of elements. So we're already starting to define mathematically what these sorts of definitions mean, right? So we have a basis for defining this in terms of set theory. Okay. Any questions or doubts so far? Okay. So we have to talk about the universe. So the universe is rather large, expanding, and so forth. So when we think about knowledge representation, our goal is somehow to describe the universe. So we could describe any aspect we would like, or make claims about any aspect that we would like of the universe. The universe is quite complex, so in order to work with it mathematically, to simplify matters, we're going to define the universe as a set, right? This is essentially somehow the set of all things we could talk about, right? So this is the set of everything. So we consider the universe to be the set U, okay? Set of all things we could talk about. Okay, QED. So we've modeled the universe. So what does it mean? We have the set U, which essentially contains all of the possible things that we could describe or talk about in our data. So what about classes and properties? So classes are interpreted to be subsets of U, okay, and then properties are sets of pairs from U. So this is the basis of our definitions. We still haven't considered any of the particular features of OWL or DFS yet, which we have to do. So we have the universe, which are all the things we describe. So how do we describe them? The first thing we need is a set of terms, a set of ways to name things, right? So we have vocabulary, which we will consider to be simply IRIs. Okay. So I will skip I'll just leave aside the literals and the blank notes. They're not important to the main concepts. So triples, if you're familiar with this notation, it means V times V times V. You can think of it in terms of Cartesian product in databases. So this would be the product of the sets, which means we take all the V's and we multiply them by all the V's and we multiply them by all the V's, which gives us somehow triples, gives us elements of 3, where each element is an IRI from the vocabulary. So we have triples, which are triples of IRIs. And we have a graph, and this notation here is used to refer to somehow the set of all triples. Okay. So we have our data and we have our universe. Okay, so we have the things we want to describe and we have some ways to describe them. We have ways to name those things. We have ways to combine those names into claims forming triples. And then we can take a set of triples which forms a graph. So how do we relate these data to the universe that we saw previously? So what we need is something called an interpretation. Okay? So an interpretation essentially is this idea of interpreting the data. So we have this interpretation I, fancy I, looks maybe a little bit like a J, but interpretation I of the vocabulary V. So what is this interpretation? We can consider it, it has 3 elements effectively. It has something to represent the universe. It has something to represent individuals. It has something to represent classes, and it has something to represent properties, to interpret properties, to interpret classes, individuals. So use the set of everything. Okay, so this is all the things that we might like to talk about, because this forms part of the interpretation. I maps a vocabulary term from V. Okay, so we have a set of vocabulary to an element of U. So we'll call this the interpretation of individuals. Okay, so what does this mean? It means if we interpret a name, we get some element from the universe. Now, in terms of mathematical definitions, we don't really care what that element is, right? just for the moment, we're going to define that it must map to some element of the universe. So every name is interpreted to be an individual. So if we think of the interpretation of individuals, you might guess that the interpretation of classes, which we can also name with vocabulary terms like person or movie and so forth. If we interpret names of classes, what we get back is a set of elements from the universe, a subset of the universe, right? So we see here some examples. We interpret person to be all the elements of the universe considered to be people. We interpret the class Godfather to be all the set of all of the elements of the universe that are interpreted to be Godfather. P maps then a vocabulary term to a set of pairs from U. So this is the interpretation of properties. So what does this mean? It means that if we interpret, for example, a parent property, that we would get back sets of pairs in the style. Or if we interpret the sibling property, we would get back the sets of elements from the universe that are considered to have a sibling relation between them. Okay, so this interpretation we've defined, let's recall, we've defined the universe, which is just a set of everything that we might want to describe. We've defined the data in terms of, we have vocabulary, we can combine those terms into, which are just terms. We can combine those terms into triples and make claims, and sets of triples form a graph. So we have the universe, we have data, and we have an interpretation that allows us somehow to, takes the universe, it takes all the terms in our data, and it allows us to map the different elements of that vocabulary to interpret them in different ways. Excuse me, to interpret individuals as elements of you, to interpret classes as subsets of you, and to interpret properties as sets of pairs from you. Okay. So we just interpret terms, right? But we still haven't interpreted graphs, right? So not even triples, right? We just interpret a single term, a single class, a single property, a single individual. How do we interpret data, real data, and not just terms? So we need to talk a little bit about models. Any questions or doubts at the moment? Perdón, el audio muy bajo.
Sorry, I didn't catch the difference between an interpretation and a model.
An interpretation and a
model.
A model. Okay. So the models we're going to talk about in a second. Where did you catch the word model? Actually, had I mentioned model? I might have mentioned it. So the short answer is an interpretation. A model is effectively an interpretation that satisfies certain conditions. So a model is something that somehow fits what you describe. So the interpretation at this point here, it could say anything. It can map anything to anything, right? So it's just, you know, this structure here. So a model is an interpretation that fits what we've stated in the ontology. So I'll describe that in a second. I'm not sure if I use the word model. I shouldn't have. I may have said that, but we'll get to models soon.
Thank you.
Okay. Okay. So any other questions or doubts? Okay. So models. How do we define what is a model? So we will assume that our RDF graph uses the vocabulary V. So we'll just assume that all the triples use some term from the set V. Okay. So we have an RDF graph, and it uses all of the IRIs that we've seen that we have in V. Or it uses a subset of the IRIs we have in the vocabulary. So we have an interpretation as well of that vocabulary, as we previously defined. So it maps individuals again it maps vocabulary terms that are individuals to elements of the set U. It interprets classes here as subsets of U, and properties as sets of pairs from U. So we say that I is a model of G. So it's essentially an interpretation or a model. The idea is that it's an interpretation that fits what we describe in the RDF graph. Okay. So we say it's a model of G if and only if. If the triple is in G, then the interpretation of the subject and the interpretation of the object form a pair in the interpretation of the property. Okay. So it means that, for example, if we go back here, if we interpret Vito and Michael, that they will be in this interpretation of the property here, parent. So this is how we now define, we start to define, what interpretations, what possible explanations what possible worlds can explain the data in a way. So how do we define the semantics of types? Well, if we have, for example, that S and O, the interpretation of the individual S and the interpretation of the individual O are in the interpretation of the property RDF type, which is a special property that we have in the standard, then what do we conclude from that? We can conclude then that the interpretation of S must be in the interpretation of O as a class. Okay. So there's maybe one slight complication here, which is that we interpret O as an individual here, as a thing, okay? And then we interpret O as a class here, which is all of the elements representing that class, which is perfectly fine, right? So if O is a class and we interpret it as an individual, it's just a thing, right? That we have that Godfather image somehow representing the class. If we interpret it as a class, then we get all of the elements that we believe to be in that class from the universe. How do we define the semantics of subclass? Well, here now we have these elements like C, O, for example, or P, S. These are sets, okay? Mathematical sets like you would have seen before in other parts. So how do we define subclass? We just say that the class of S, interpreting the class of S, it's a subclass or subset or equal to the class of O. Okay, so if we see this triple here, subclass of S and O, then we say that the class of S is a subset of the class of O. How do we define the semantics of subproperty? It's the same thing. We define, if we have S as subproperty of O, then we define that the sets of pairs in S are a subset or equal to the set of pairs of O. How do we define the semantics of domain range? So we can continue in this way, and what we end up doing is just defining all of the vocabulary in terms of set notation, in terms of set theory, right? So we just say that if we have this domain element here, if S has domain O effectively, then what we're going to infer in this notation is a little bit awkward. I'm using here, just to abbreviate it, relational algebra, which is a projection. So this says just project the first element. So what this does is it takes all of the pairs for the subject S. Okay, so we're interpreting S to be a property that gives us a set of pairs. We take the first element of every pair, and then we just say that that is a subset of the class denoted by O. For the range, we do something similar, except for we project the second element of each pair in this set here, and define it to be a subset or equal to the class O. So the specific definitions are not so important, but excuse me, hopefully you're getting the idea of using the set theory and set notation to define precisely what these things mean. So to continue with some other examples, what about OWL? We just had a look at RDF and RDFS vocabulary. How could we define, for example, the semantics of same as and different from? This one's same as and different from are quite straightforward. So if we have that S same as O in the data, then we say that the interpretation of S and the interpretation of O have to be equal. The element that both of these things refer to have to be the same. So this gives us the notion of two names referring to the same thing. Different from, if we have a different from relation between S and O, then what we want to say is that they must be different. They cannot refer to the same element of the universe. Okay. How do we define inverse properties? We define inverses by saying, okay, if we have S is inverse of O, then for all of the pairs associated with S, the inverse, if we swap the two elements, then they must be in O as well. Not only that, but all of the pairs in O, if we swap them, they must be also in the interpretation as a property of S, right? So it works in both directions. How do we define transitive properties? We continue in this way, right? So we say for all x, y, z, we're all x, y, z. Then if x, y is in the interpretation of S, and y, z is also in the interpretation of S, then we're going to imply that x, z is in the interpretation of S, and so forth. So with disjoint classes, this was relatively straightforward. We say that the interpretation of the two classes is the empty set. So essentially the intersection, of the interpretation of the two classes is the empty set. This defines the disjointness, and so on. So what I would like to get across is this idea of how we can start to define the different features. And essentially these different features impose requirements on the interpretation. It says that if we have this in the interpretation, then this must hold, right? Or if we have this in the interpretation, then this must hold. So this starts to somehow define interpretations that model the data, interpretations that fit the data, that fit a particular graph, right? So a model is essentially an interpretation that fits the graph. Excuse me. Any doubts or questions? I'm going to try to explain that with some examples and give some ideas. And then we can maybe take a break. So a model is any world that an ontology might describe, okay? So what this means is essentially that this is very conceptual, because we talk about a world as an analogy, but really what we have is a bunch of sets and sets of pairs and elements. We don't really, it's just a mathematical abstraction, but it's sort of a useful analogy to think about this idea of an ontology being a possible world. A model being a possible word that an ontology might describe. So why is this useful? Where are we getting to? So it allows us essentially to understand, to somehow interpret an RDF graph, for example, and to think about it in real terms. In practice, it's humans, it's us people that associate these meanings, to say that Carmela refers to this character in the movie, for example, or this person. We give this mapping. But in terms of mathematical notation, it allows us also to understand the consequences of an ontology. So first of all, a model is any world that an ontology might describe. And here we have essentially that Carmela has child relation to Michael, ancestor of relation with Michael. Michael has daughter, has child, and ancestor of Mary, okay? And we have various definitions here: has daughter, subproperty of has child subproperty of ancestor of type transitive property. Carmela has child Michael, Michael has daughter Mary. So we see essentially what we've represented is are the relations about the individuals. So there's one thing here that we're missing from this model, where we see ancestor of is of type transitive property. Okay, and we have Carmela Michael, ancestor of, we have Michael Mary, ancestor of, which should give us that Carmela is the ancestor of Mary, right? But we don't have this. So essentially we say that this is not a model of the data, because essentially we have to describe a world, and in our world, if something does not hold and we describe it, we say in our data that it's true, then that's no longer a world that we're describing. So here, for this to be a model, then Carmela needs to be an ancestor of Mary. Now we have a model of the ontology for the L semantics. So I think with that, we could take a break of 10 minutes. Any questions or doubts thus far? Okay. Oh no. Shift F5, Shift F5. Okay, I just pressed F5. You can see as well, by the way, there's some hidden slides that I've cut that are not, they're kind of side issues that I've cut to shorten the class. So if you look in the PowerPoint, you might find some hidden slides. Main goal is to keep the class shorter. So entailment. This is a key notion, really. This is the notion that we're most interested in. This is sort of the application of these notions of models, interpretations, and so forth. So it's a slightly counterintuitive thing, because as we add data, as we add definitions, we add a new definition, we think about it as building up data, right? And building up consequences and finding out more things. When we talk about models, we have to think about it in the almost inverse direction. So at the start, before we define anything, it's like any model is possible. Okay. And as we add the axioms, as we add more definitions, fewer worlds are possible. So we're shrinking the possibilities. So it's similar to this quote by Michelangelo, this idea that you take a block of stone. At the start, anything is possible, right? And then you somehow start with your axioms, you start removing the things that are not true. This is how it looks like from the model theoretic, this model-based way of defining the meaning of data. So we start, at the start, any world is possible. And only as we start to define things do we bring down the number of worlds. So, or the number of models, right? So the fewer the models, the more specific somehow our ontology, or what we're describing about that world. Okay, so it's useful to keep that in mind. So we can use that notion then for entailment, okay, which is the same as inference. Use the word entailment for the relation. So to say an ontology O entails another ontology, we use the term inference to say somehow that an algorithm can somehow apply inference. It's an algorithm, let's say, with respect to entailment. So, okay, we have an ontology here in yellow, which states that has daughter subproperty of has child inverse of has parent, subproperty of ancestor of. Ancestor of is a transitive property. Okay, so we have here some data. We have Carmela has child Michael, from which we could probably see that has child, okay, this doesn't help us, but has child inverse of has parent. So we would expect this ontology to entail that Michael has parent Carmela, okay? And then we see has child subproperty of ancestor of, so we would have Carmela ancestor of Michael, and so forth, okay? So the question then is, do these triples here, does this ontology effectively, when we talk about an ontology, we talk about essentially an RDF graph with special meaning. Does this ontology entail this one here? Okay, which means does this do the triples here follow from the definitions in this ontology? So how do we define that? We define that by saying that any model of O is a model of O prime. Okay, so we say here that they do entail, that this ontology does entail it. Michael has parent Carmela comes from the fact that Carmela has child Michael and has child inverse of has parent. Michael has child Mary, that comes from the fact that has daughter subproperty of has child. Carmela ancestor of Mary, that comes from the fact that we have the two has child relations, and then we apply the transitivity and we get that Carmela as the ancestor of Mary. So we see that this ontology follows from this. How do we define that formally? We define that any model of O, any possible world that O is describing, is also a possibility for the ontology, right? So somehow this ontology here has more details, it's more specific, and therefore it permits strictly fewer worlds than this ontology. Essentially, any world that's possible here, yeah, or any world, sorry, that is possible here must also be possible here. Okay, so the models that this ontology, which is not as specific it will permit more possibilities. Okay. So essentially, what we say is that the models here are a subset of the models here. Okay. So again, it's this idea that as we add more and more specific data, we remove possibilities, possible worlds that the ontology is describing. And we use this symbol often for entailment to say that this ontology essentially entails this other ontology here. So this is the entailment relation. So ontology entailment, we'll take maybe an example or two. Does O entail O prime, right? That's the question. So in this case, no. Why do we, intuitively, let's have a look and see. We see that Mary likes cake, okay? But we don't see anything here that might indicate that Mary likes cake. There's nothing that from which this statement follows. The fact that Carmela is an ancestor of Mary doesn't appear to follow either, right? So there are models essentially where of O that are not models of the ontology O prime. And essentially here we have a model of O, okay? So we have some description that fits the ontology O. Michael has parent Carmela. Apologies. So in this case here, this would need to have the has parent relation. So this is fine, but the has parent relation is missing. So the, yeah, I would have to change that data. But essentially the idea would be if we had the has parent relation here, then we have Michael has child Mary, we have Carmela ancestor of Mary. So somehow this model fits this ontology here, but it does not describe that Mary likes cake, right? So essentially we do not have this entailment because this model here is a model of this ontology, but not of this ontology here. Therefore, this ontology does not entail this ontology. This ontology permits possibilities here that are not possibilities here. Right? We describe different worlds. Any questions or doubts?
I got a doubt. So Mary likes cake is a model that is on O prime, but it's not in O. So why doesn't we say that O does not entail O prime and not vice versa?
So in this case, both hold. So neither entails the other. In terms of the entailment relation, what we're saying is that essentially we say that O does not entail O prime. We could also say O prime does not entail O, but in this case, we'll focus on O does not entail O prime. So what we're saying is that there are models of O, there are possible worlds that it describes that are not models of O prime. So what that means essentially is that there are possible worlds that this thing describes here that are not modeled. They're not that the second graph does not describe. So for example, if we were to start with all things are possible, and then we just say Michael has parent Carmela, and we somehow remove certain worlds. We now at least need some individuals that have some relation that we can map to. So that already removes certain worlds. So as we're adding more axioms, as we're getting more specific, we're removing possible worlds, okay? So we'll have to think that in general, an ontology will entail another ontology that's less specific, that says less. It somehow says strictly less than the ontology here. So we say that this ontology here entails this ontology here. Somehow this is as specific or more specific. It says more things, right? And somehow this is a subset of the things that we can know from this ontology. So given that this is more specific, it means that essentially we are removing, we have a smaller set of possibilities, okay? So if any of those possibilities, if all of those possibilities are also possible in the other ontology of the models, they're also models of the other ontology, then somehow this does not restrict any of the possibilities, right, of our possible worlds. So we say that if any model of this is also a model of the second ontology, okay? Then if we were to add this ontology, if we were to take the two together, for example, we don't change the possibilities, right? We still have the same set of possibilities defined by the more specific ontology. So this is the more specific one. This is the more general one. This has fewer models. And if we were to add all the data here, we wouldn't change the models of this one, right? We haven't said anything more specific than what we had already said in that ontology. I understand it's kind of a bit weird, but hopefully that helps to clarify a little bit.
I think that yes.
Yeah. Okay. So again, it's important to think that the more specific ontology will entail the somehow less specific ontology. The more specific ontology will permit fewer models. Okay. And therefore, the models that we have here are more because there's more possibilities, right? So somehow, if every model of this one is contained in the models of this one here, then somehow it doesn't say anything new. Somehow, if we were to take the, we're not going to remove any models if we take the union of these two here. Okay. Okay, so what can we do with this notion of entailment? So we have some reasoning tasks we can consider. And the first and most obvious thing, and what we've seen in the labs, is called materialization, okay? Which is essentially the idea that we have this ontology, we have some semantics, some definitions in there, and we can see that there should be some entailments that come from that ontology. So the idea of materialization is just to write down entailments. So we just start writing down all of the things that hold, okay? So again, when we start writing down these entailments, essentially it means that this ontology here entails this ontology here, and we start to somehow describe the maximal ontology that this ontology entails. Yeah. So we just start adding all the things that we can conclude from the ontology here. For example, Michael has parent Carmela. That follows from Carmela has child Michael and has child inverse of has parent, right? But we'll quickly run into a problem, right? And the problem is that if we look at some of the definitions here, we see a person is equivalent to having two values on the property parent from the class person. Okay. So what will happen here? We have Mary as a person. So if we try to write down the entailments, what will happen is we'll reach this definition and we'll see that we can start to define that Mary, okay, Mary is a person and people have two parents that are people. Mary must have two parents and those parents must be people, and we can represent, even though we don't know who the parents are, we can represent them as a blank note that they exist. And these parents, given that they're people, they must have parents that are people. So we have parent 1, 1, parent 1, 2, parent 2 has parents 2, 1, parent 2, 2, parent 1, 1 has parent 1, 1, 1, parent 1, 1, 2, that are people, and so forth. So we see that we create this infinite chain of possible entailments. The point being that the entailments are not going to be finite all the time, so it means that we are not going to be able to write them down. So this is a little bit, this sort of maybe gives us the idea that we're not going to be able to do complete reasoning by just writing out all the entailments and then storing them and then running queries over that data, for example. It's not going to be possible to have a complete way of doing that. Okay, so we could also infer, for example, some weird things here that, if person is equivalent class qualified cardinality 2, then person is subclass of max qualified cardinality 2. Each person has at most 2 parents that are people. Each person has at most 3 parents that are people, and so forth, right? So we could also start to entail these sorts of definitions here. So yeah, we'll quickly get an infinite number of things we could possibly write down, right? So that's not going to work very well. Materialization does work, but we won't be complete with respect to very expressive ontologies. So it works well for RDFS. For OWL, we can do some incomplete reasoning, but we won't get everything that an ontology entails. So what's the way that, what's a second task? A second task would be called ontology satisfiability, right? So we're not actually checking entailment in this case. What we're asking is, does O have any model? Okay, is there any possible world described by O? So you might think, well, sure. I mean, every ontology must describe something, right? But in some cases, we can have ontologies that have no possible model. And that's because they contain a contradiction that essentially excludes all possibilities, right? So a contradiction or an inconsistency. So we have two definitions here, for example. We don't have any data, right, for the moment, but we just say that a person is equivalent to having two people on the property parent, and we say that a first person is a person. Okay, so we have some data, and is an element of the class that has two two apes that are parent. Okay, so a person has two parents that are people. First person is a person. It has two parents that are apes. Okay, so now the question is, can we construct? Is this possible? Can we construct some possible explanation, a possible model for this ontology? Can we see a possible configuration of things that this describes consistently? It's a bit of a weird one, right? But we might think that, okay, first of all, looking at this here, we know that since first person is a person, it must have two parents, and it must have two parents that are people, right? And we see here that so essentially now we know the first person has two parents that are apes. So can we reconcile these two different definitions? Well, one way is that we never said that persons and apes are disjoint. So the parents could be both people and apes. We never said that a person or first person, a specific first human, have only two parents. They could have two parents that are apes, two that are persons, and so forth. So does O have any model? In fact, it does. Okay. So in this first model here, we say that first person has two parents, okay, that are different elements of the universe, okay. And then we say that both of them are people and apes at the same time, okay. And we see that we satisfy these definitions here because the first person has two parents that are people, and it has two parents that are apes, okay. So that's one possible model. What if we add that ape is disjoint with person? So now that we say that something cannot be an ape and a person at the same time, we rule out this trick of just saying the parents are of type person and ape. But if we rule out that possibility, we still have another model, which is basically that now first person has four parents, okay? And two of those parents are apes and two of those parents are people. Again, when we talk about qualified cardinality, we only count the things that are in this class. So in no part of this ontology here have we defined that first person only has two parents. Okay. So first person can have two parents that are apes and two parents that are people, and we have a valid model still for ontology. Okay. So the ontology O is still satisfiable. There is still some way of drawing out a model that's a model for the ontology. Okay, so what would we have to add to O to make it unsatisfiable? What would we add to make it so that we can't possibly just create a world that this ontology describes? One thing would be to say that people have at most two parents. In that case, if we rule out this trick here. Okay, so now first person has to have two parents. Okay, it has to have two parents that are people and two parents that are apes, and apes are disjoint with people. So you can think about how to maybe find another trick, but you'll probably convince yourself that it's not possible if first person is only allowed to have two parents, and the parents can't be both person and ape at the same time. We could define, for example, that all of the parents of people are apes, or all of the parents of people are people, right? In that case here, we would infer that since first person is is a person, actually I haven't added that here, but first person is a person, then we know that these two parents here, all of the parents of first person must be of type person, and then we know somehow that D is an ape and a person, which contradicts the disjoint. Okay. Or first person is an ape, because we know that first person is a person, and something cannot be a person and an ape at the same time. So essentially, when we talk about unsatisfiable ontologies, they're effectively ontologies that have some contradiction. They can't be satisfied. It means they can't have a model. Okay? So the models satisfy the ontologies. We say that a model is an interpretation that satisfies an ontology. So if the ontology can't be satisfied, it means it has no model, and that's because it has some sort of contradiction, some inconsistency. Right? Or first person and nothing. Okay, so there's a class which is the class of no elements, okay, now, which is nothing. So any sort of inconsistency would make an ontology unsatisfiable. But what I would like to get across here with this example is that it's probably not obvious at all whether or not an ontology is satisfiable or not. This example here requires quite some thinking. Yeah? Even here, it would be worth kind of proving somehow that it's unsatisfiable. But the idea of these reasoning tasks is that we don't have to. We can use a tool, a system, to check if something is unsatisfiable. So you could consider trying to model the data of a complex domain like medicine. You're describing different diseases and different illnesses, medications, and so forth. And then you can use ontology satisfiability to check if what you've described is even coherent, if it's consistent, or if it has some contradictions based on what you've defined. And people have used this also, for example, for modeling laws, to see if laws are internally consistent or not. So this task on its own is also quite useful, this idea of satisfiability. So an unsatisfiable ontology cannot model any world. It is effectively inconsistent. And this is why in the last class I was talking about the world imploding. Essentially, we just end up with this case where we describe no possible world. Okay. So another reasoning task, sorry, maybe a question or a doubt, if you have questions or doubts about satisfiability, it would be good to know. Good to address them now. So what's interesting as well about ontology satisfiability is that we can define it again in terms of models, right? So this again, we're using the term of model to define this task that we can use in practice to see if what we're describing is coherent, consistent or not. Another task that we have is entailment checking. So given two ontologies, does ontology O entail ontology O prime? Okay. So again, we've already defined this, are all models of O models of O prime as well. Okay? So this is another task that we considered that we discussed previously. So we're given two ontologies and we check if the first entails the second or not. So we looked at three tasks. There are other types of tasks we could consider, but we looked at materialization, write everything down. We looked at satisfiability, essentially, is the ontology consistent? And the third one, does one ontology entail the other? Right. Okay, so these are tasks. These are things we would like to be able to do with our ontology once we have our nice ontology defined. What about reason? So how do we implement this, right? We sit in front of our IDE in Java and C, and we're going to implement these methods. Where do we start, right? What sort of approach are we going to take? So does the ontology entail O prime? How could we implement this, right? So this is quite not straightforward to implement. An easier thing to implement is to check unsatisfiability. So what we're going to say is that O entails O prime. We can use this observation that if O entails O prime, if and only if we take the union of O and not O prime, if this creates a contradiction. Okay. And one way to perform entailment then is just to reduce the problem of entailment to satisfiability. And that way we can just implement satisfiability and we have entailment automatically. So it's like A entails B if and only if A and not B is false, is an inconsistency. Okay, so how does this work? It works by saying, for example, that ontology O entails O prime here. Michael has child Mary, which we can see is true, okay, based on these definitions. This entailment holds if and only if this thing here is unsatisfiable. What's this thing here? It's O, like we had before, and we also add not O prime. Okay, so we add in here this slightly strange syntax here to say that Michael does not have the child Mary. Okay? And if we get a contradiction here, if this is unsatisfiable, then we know that O must entail O prime. Okay? So if we create some sort of inconsistency here, when we negate O prime and add it to O, then we know that O entails O prime. So we can reduce entailment to unsatisfiability. Okay. So how do we test unsatisfiability then? So essentially the question is, okay, we know we have entailment, we just have to, if we have unsatisfiability, we don't need to implement entailment. How do we implement unsatisfiability then? So the short answer is that in many cases we can't. It's impossible to implement unsatisfiability in the general case. So I will have to continue this on Wednesday. So what I would like to talk about is a bit about undecidability, this idea that there are certain things that we can implement them, but as algorithms, but the algorithm might never terminate. So we'll talk about undecidability on Wednesday. I'll continue the class. And we'll talk about why this problem is undecidable. Okay. So yep. Any questions or doubts? Okay.